So it's 2 o'clock where I am, and we'll get started, and hopefully anyone who hasn't joined yet can join without too much trouble. I want to welcome you to this seminar. It's on partial discharge, its causes and effects. We're going to spend a lot of time on that because it's very misunderstood. And we're going to talk a little bit about online detection techniques. So by online, I mean with the power system energized, direct connection and indirect connection methods, but mainly indirect connections where you are not making an electrical connection to the system, but you're still able to detect the PD. So that's what we're going to talk about today, and we'll get into it. The presentation should be about 45 minutes, and we'll open it up to questions. And to be honest, we can keep going as long as you have questions. There's no hard stop on this. Just so you know who I am, my name is Bill Higginbotham. I run EA Technology for North and South America, and responsible for everything that that title would imply. Do a lot of PD training, seminars, testing, a little bit of everything. Some logistics for today. If you have any questions, type them into a chat box. If you have something urgent, type it in the chat box. I'm not going to be monitoring that, but we have a moderator who'll be looking at it, and she'll alert me if we've got any major problems like slides not showing up. And then we'll go through the questions at the end of the presentation. When we're all done, you will be getting a copy of the presentation, and within a couple days, we'll have this entire video available on our YouTube channel. So first, a little background on EA Technology and who they are. So EA Technology was developed as the research and development center, the problem solvers for the UK power system when it was nationalized. It was all one utility. We were basically the EPRI of the UK. We solved whatever problems the power system had. In the late 90s or the early 90s, the power system in the UK was privatized. National Grid was formed as a transmission company, and distribution companies and generation companies were all split up, and EA was split off as a separate standalone company. Still doing a lot of the same things, solving problems, but we've become mainly an asset-centric company. Our specialty is in asset reliability for medium and high voltage. We do a lot of work in there. We build instruments, we do consulting, we have software, we have an oil lab, we have a SF6 lab. We do a lot of work in the asset management standards of ISO 55000 and originally PAS 55. All that serves to give us a good background in what causes assets to fail. And so hopefully that gives us a little insight that I'm going to try and share with you today. That's my last salesy slide. So partial discharge, what is it and why do we care? Well, we're going to talk a little bit about why we care because it is very misunderstood. Every time I go out and I give a presentation, I hear views from people that don't match up with the reality of what PD really is and why we care and how you detect it and that. So we'll spend some time on that today. So where can it occur? The physics say that it can occur at any voltage. Practically, it doesn't occur much below 3.3 kV, 4160, somewhere there, and as high as you want to go. Highest I've ever worked is 769, so I put that. Where can it occur? Partial discharge is a phenomenon that occurs on insulation. So anywhere you have electrical insulation and you have a high stress electrical field. It's very common in metal-clad switchgear, any kind of indoor or outdoor insulator that you might have, whether it's a pole top insulator or a station post insulator or a bushing on a transformer, anywhere you've got insulation. Transformer cable boxes is a great place. They tend to be closed up. They tend to have high humidity at times, and they can be highly susceptible to PD. Cables, in the middle of the cable, in the termination of the cables, down in underground vaults, high humidity is an issue, so you get a lot there. It can occur inside the transformer. It can occur in the oil. It can occur in the SF6. It can occur in dry type, cast resin transformers. So really anywhere you have insulation, you have voltage. Typically, we kind of limit it to the 3.3 kV and higher because at lower voltages, while it may occur, it takes so long to lead to failure that it just doesn't pay. And to do testing and to try and prevent it in something at below 2,500 volts, you're better off waiting until it fails. So I get this question all the time, is partial discharge real? Here's a little video. Hopefully it plays well for you here. So you see that spark. That spark is a result of partial discharge. Now, it's obviously not a complete flashover. I think that was 11 kV switchgear that we were looking at there. A full flashover would be much more dramatic. So the Wikipedia definition is a flashover of part of the insulation system due to a localized electric field greater than blah, blah, blah. You can read as well as I can. But what it is part of the insulation can't withstand the electric stress on it. Not the whole insulation, but just a part. And so what happens is that part flashes over. Now you've got enough remaining insulation in your system to not completely flash over, but that one little part is the issue. And here's a great little schematic representation that helps explain it. So if you look at this, I've got a conductor and a ground. So I've got my two elements of any high voltage system, and I've got this green stuff, which is the insulation. And that could be air, oil, SF6, cast resin, I don't care what it is. But I've got this insulation, and I've got some part of it that can't withstand the electric field. So in this case, we're calling it a void, so it's solid insulation. And that void is represented by C2. So if you think about any insulation system, and if you do a lot of work with cables, this is obvious, but the insulators can be represented as a set of series and parallel capacitances. Every insulation has capacitance because the definition of a capacitor is two conductors with an insulating medium between them. Well, that's what we've got. So to keep life simple, to keep my math simple, I've got three capacitors. They're all the same value. Let's call them, I don't care what we call them. And as the sine wave voltage is increasing and decreasing nice and slowly at 50 hertz or 60 hertz, the voltage across those capacitors is dividing nice and evenly. So let's say at a peak of 3,000 volts, I've got 1,000 volts on each capacitor. And let's say our void can only handle 999 volts. So what happens when we get to 1,000 volts on C2? That void flashes over. That's that spark we just saw in the video. That's that discharge. And so that one part of the insulation discharges, which means the gases around it ionize, the voltage on it drops very quickly from, say, 1,000 volts or 999 close to zero, as fast as the capacitance will allow. Now, we still have 3,000 volts between our conductor and our ground, so how are we resolving that issue? The voltage across C1 and C3 has to change to 1,500 volts each. The only way we change the voltage on a capacitor is to flow current through it. So what the partial discharge results in is a current pulse from conductor to ground or ground to conductor, depending on our polarity, to equalize the remaining charge on the remaining insulation. And so we get this high frequency unidirectional current pulse as a result of the discharge. So that's the science behind it. We get this pulse, it's very short, it's in the microsecond range, can be in the nanosecond range, typically a microsecond or so. It can be, milliamps, hundreds of milliamps, not a big high energy event, but it does occur. Why does this occur? And say I've got insulation, I've got this nice solid insulation. Why would this occur? And the reason is whenever you have a change in the dielectric constant of a material, that changes the electrical distribution. So this top picture, I'm showing a homogeneous insulator. I've got my equipotential lines, which are the blue horizontal lines. The voltage drop is consistent all the way through the material. Now, if I had a void in the middle of that material where the dielectric constant is very different than the rest of the insulation, my voltage distribution will change. And the result of that is I have a higher stress level where I have a lower dielectric constant. So the void is going to have a much higher voltage across it, and that's going to cause it to spark over. So this is one of the reasons you see discharge in internal voids in, say, XLPE cables or any kind of cast or molded insulation where you might have defects like inclusions and dirt, things like that, electrical trees. All that changes the electrical distribution and increases the stress on the defective part. we like to talk about PD in four different types. And the first one is corona discharge. So this is a term people use interchangeably for partial discharge, that I've got corona, I've got a corona device. Corona is just one form of PD, and it's actually the least harmful form of PD. So what corona is a discharge into a gaseous dielectric, air typically. So if I have a EHV substation and I have a sharp point sticking out of a piece of bus bar, or I've got a bolt that sticks out of a bracket or something, and that bolt, right at the tip of it, because it's sharp, it's creating a concentration of field stress. And that stress exceeds the dielectric capability of the insulation, the air. And so what happens is the air decomposes, it turns into oxygen and nitrogen, and we get a discharge, we get current flowing out into the air. And that's corona, okay? And corona has the positive effect in that the insulation we're destroying is air molecules. So we got lots of air molecules, the air molecules are replaced, and the discharge does not build up, does not cause continuous damage, and does not lead to flashover. It creates ozone, it creates nitrous oxide, it creates electrical noise, it wastes power, but it doesn't lead to catastrophic failure. So we want to be able to identify corona discharge and don't mix it up with the other types of discharge that really bother us. The second type discharge is surface, and this is where the discharge, that current path, is across the surface of the insulator. And this is the most common. It probably makes up 90–95% of the discharge we see in the world. It's the fastest moving, it's the most destructive, but it's also the easiest to find and the easiest to fix. So there's pluses and minuses. Whenever you see that tracking or treeing, you see that carbonization. I've got some examples I'll show you later on. That's surface discharge. Internal discharge is particularly painful because it's hard to find. It's hard to see. There's nothing you can inspect. There's no other test you can do other than a partial discharge test. You can take something apart, clean it, service it, put it all back together, and it can blow up the next day. So you've got to be able to detect that. We'll talk about how you detect that. Contact discharge is another kind of side version where you've got floating metal, or you've got too short a gap in an air insulation, and you get discharge from the conductor to another piece of metal. And it's sometimes called contact discharge, sometimes called floating metal discharge, but that causes a very high signal for you to detect. But again, we're not damaging the insulation, so it won't typically cause a failure unless the buildup of ozone and that causes your failure. It's a real high level, it's very characteristic. Our concern with contact discharge is that because I've got that, it's so high that it might hide some of the other types of discharge that I am trying to find. So we'll talk about these four types of discharge and what we do about them. What causes PD? So we said, well, it's when part of the insulation can't withstand the voltage, but why would that be? When would that happen? Surface contamination, salt fog, conductive materials. Steel mills are horrible for this. Paper mills, you get dust and lots of water in that. So that kind of surface contamination on the insulator, it's real common. You live on the Gulf Coast, you can go out and look at the high voltage lines. After a salt fog, you'll see it there. Workmanship. This we see very often in cable terminations. Someone does a poor job of terminating the cable. They create a high stress environment somewhere in that termination and leads to discharge. Manufacturing defects, that's typically where you've got cast resin stuff in that, and there's air bubbles in that casting. Sometimes you can get it in extruded cables. It doesn't happen very often, but it does happen. Wrong parts for the job. That's unfortunately happens quite a bit, where they'll use the wrong parts, so they'll put stuff closer together, they use the wrong boots. Happens too frequently. Salt spray, salt fog, well, that's going to contaminate it. Mechanical damage, very often you'll see something damaged when it's installed, the pulling technique of the cable, or we'll see very often in buried cables and wind farms and that, where they're not buried in sand or in a nice media, they're buried in whatever dirt was there, and rocks cause pressure on the cable, and they pinch the insulation. That happens. And then things do get old. Electrical stress does cause physical changes to the insulation, and over time it can cause paper oil cables to dry out, it can cause insulation to break down, and it does wear out. It takes a long time, but in a high stress location, it could happen faster than in other locations. So there's a lot of things that happen when you have partial discharge. And so I want to talk about these. I'm going to kind of talk about them in random order, but you've got electric effects, you've got electromagnetic effects, acoustic, which is sound waves traveling through air or through solids, but they're sound waves, not radio waves. Electromagnetic is radio waves, acoustic is sound waves. And then we also have gases. So I talked a little bit about the gases. So if you have surface discharge or corona or contact discharge, you have this spark that occurs inside air. And the effect is the generation of plasma. And plasma is basically the atoms getting ionized. And so you're taking the air, which is mainly oxygen and nitrogen, and breaking it down into its component elements. So the oxygen becomes ozone, and the nitrogen becomes nitrous oxide. And by themselves, they don't necessarily lead to damage. Ozone is not great. We all know the effects of ozone on plastics and that. Nitrous oxide, however, once you subject it to a little bit of humidity, it turns into nitric acid. And nitric acid loves to eat through insulation. When it eats through this insulation, our discharge site gets more damaged. And so now we have a bigger discharge site, which generates more nitrous oxide, which creates more nitric acid and leads to failure. So while we can't necessarily use the gases as a detection method, they are really a big cause of failure. Now, sometimes you go into a substation, and so certainly an enclosed substation, you can smell the ozone. That's an indication that you've got a concern. So that's on the gas side. On the acoustic side, we have these sound waves, and they're generated by surface discharge, corona, contact discharge, not internal discharge, as you might imagine. It's occurring inside the insulator, so you're not really going to see that. You're not going to hear it. But it creates a lot of energy in the ultrasonic band, which is above the range of human hearing. I've got a nice green circle around that because that's one of our detection techniques we're going to use. We're going to listen for ultrasonic energy that's characteristic of PD and use that as a detection method. When it's really bad, and I've walked into a couple substations that are really bad, first you smell the ozone, and then you hear the crackling, and you hear the buzzing, and you can actually hear discharge occurring. That's approaching time to run. You're on the verge of catastrophic failure when it starts getting into the audio band. Continuing to move to the left, we've got electromagnetic. So we've got a couple things happen. One is light. As you saw in that video, you can see it. It's a spark. It's a visible spark. But unfortunately, we don't always have line of sight to the spark, and we don't want to stick our heads in the switchgear, and we don't want to go out climbing a pole in the middle of the winter to see this discharge. So light isn't so good as a detection technique, but it is there. It does create a fair amount of light in the ultraviolet band. And so if we have a specialized device like a corona cam, I can see corona from a distance by just detecting ultraviolet and converting that to visible light, showing it on a screen. It creates a lot, doesn't create a lot of heat. It creates heat. It's a spark. Sparks are very hot. It's plasma. Plasma, by its nature, is got to be several thousand degrees. But it's very short duration, and it's only occurring every 60 hertz every cycle, every other cycle, or every couple times a cycle. But it's not occurring very fast. So the duty cycle of the heat generation is relatively low, and we don't get a lot of heat. But we can use that as an indication that we've got a really severe problem. That heat is also going to damage the insulation. So in addition to the nitrous oxide, I've also got this very high temperature right by my plastic insulation or my paper or whatever. It's going to cause damage. So a combination of the heat and the nitrous oxide is going to cause the problem to get worse, and it's going to snowball and lead to catastrophic failure. The last thing is radio waves. So when you have discharge, anytime you have a spark, if you're driving your car in a lightning storm, what happens when you get a lightning strike, the radio gives you static. So radio waves are generated by any electric spark. There happens to be a lot in the UHF band, and we're going to talk about UHF a little bit. There are some in the VHF band. Corona tends to put out a lot in the VHF band and not in the UHF band, which is convenient for us. We're going to talk about that. And then there's a couple electric effects. First, I for current. There's that current pulse I talked about. If I can measure that current pulse, I can see the PD. And the last one is TEV, or transient earth voltage. And this is the most unbelievable thing I'm going to talk about today. But it's basically a voltage that appears on the outside of a grounded metal box as a result of discharge inside the box. So I can come up to a piece of metal clad switchgear, measure the voltage on the grounded outside of this box, and see if there's PD going on inside. A little hard to believe, but it does occur. And that's really good because it occurs regardless of whether you have internal discharge. So if you have internal discharge, I'm not going to get any ultrasonic, I'm not going to get any light, I'm not going to get anything I can measure except TEV. So TEV is really good for finding internal discharge. So what kind of methods are we going to use? I've talked a little bit about these. One is ultrasonic testing, or acoustic testing, some people call it. We're going to listen for the sound. We're going to try and discriminate the sound of PD compared to all the other sources of ultrasonic energy in a substation. And we're going to look, if we're on the outside of metal clad switchgear, we're going to try and get an air path from the source to the sensor, right? We want to listen to something, so we kind of need an air path. So we're going to listen to vents, louvers, parabolic dishes if need be. And if there is no air source, we're going to use a contact sensor that actually can hear through the metal. So we're going to do acoustic testing of some sort, TEV testing, which is this transient earth voltage phenomenon. We're going to actually measure the voltage on the outside of the cabinets. An RFCT or an HFCT, they're called that interchangeably, is a radio frequency current transformer. So if you think about testing cables or something that's going to ground, right? Our PD pulse is trying to go to ground. If I can put a high frequency transformer around that, so it's a split core transformer, if I put that around the ground strap, I can often pick up that PD. And so that's a direct measurement of the current. And the last is radio frequency testing. So if I've got a radio receiver, I can pick this up. Now, these things are not generating great radio signals, but if I have a sensitive receiver, I have a directional receiver, I can tune it to wideband or narrowband in the UHF band or the VHF band. I can play around with that and pick up this electromagnetic interference that's generated by the PD. So these are the methods we're going to talk about. So surface discharge. If I want to measure something for surface discharge, what I'm going to do is I'm going to take some sort of device, typically a device that takes the ultrasonic energy, which is sound waves above the range of human hearing, and then converts it down into a range where we can hear. So our device in particular, we take something at 40 kilohertz and we bring it down to a center frequency of 8 kilohertz, 2 kilohertz rather. And we do that with a technique called super heterodyning. And what that does is it moves the sound without changing the nature of it. So as you're listening through your headphones, and of course I've got a picture of a guy without headphones there, but when you've got a guy listening with headphones, you hear this sound. It sounds like you would expect it to. It sounds like arcing, sparking, buzzing, bacon frying, the kind of sound you would expect an electrical discharge to make, because we've just moved it, translated it in frequency without changing the nature of the sound. So we're going to listen to that. Our more advanced instruments are going to give us some more information and give us some display, perhaps a phase resolve plot, perhaps some sort of algorithm that's going to help us distinguish between noise and PD. Because there's a lot of things that create ultrasonic noise. If I just rub my fingers together, I'm creating more ultrasonic noise than PD will, typically. These instruments are very sensitive. The kind of levels that our instruments detect are on the range of how much noise your eyes make when you blink. So I can hold the instrument up to my eye and a foot away from my eye and blink and it'll register. So we're talking about some pretty quiet sounds. And what we're going to do when we're outside gear, we're trying to find a path in. So we're going to look for gaps around the gear. We're going to look for louvers, bent holes, bolt holes, gaps around doors that don't fit too well, things like that. And that's what these pictures are kind of showing. Now, ultrasonic energy, ultrasonic surveys are very much affected by the environment, humidity especially. So in a very high humid environment, it's going to be a lot worse. The discharge is going to be worse, and the transmission of sound is going to be better. So you're going to get much higher levels. If you're in a very dry period, the PD could actually stop, or the transmission of the sound is going to be a little quieter. So we want to make sure that if I'm doing periodic surveys, and I'm doing it every year in order to trend it and see if it's getting worse, I want to do it in similar humidity conditions, and I'd like to do it in high humidity if I I also want to make sure that I, keep track of that survey. What were the conditions today? What was the relative humidity? What was the temperature? So as I go back year after year after year, I can see, oh, it was a lot more humid that last year than it was this year. So I'm not too surprised that the sound went down. Doesn't mean the problem went away, but the sound might go away. And as I mentioned, it's got a distinctive crackling noise, and it can come and go. It may not occur on every pulse. It may occur on every other pulse, or it may occur on every 10th pulse. As it gets more steady, and occurs on every pulse or a couple times on every pulse, then we know it's getting worse. The severity is, so if I'm measuring a number, if I'm measuring a level, that is not necessarily related to how severe the discharge is. So you think we're talking about sound, and I'm listening to something, and if there's a panel in the way, or something that's blocking the sound, the level could be much lower, but the discharge is not. So I'm going to compare the discharge in one cabinet versus another. I'm going to compare the discharge between identical arrangements. I'm going to compare the discharge over time. Things where that path from the source to the sensor doesn't change. If the severity changes, then it could be reflected in a change in amplitude. But it's not always indicative that, okay, I've got a level of 13, I've got a problem. It's more if I've got a nice clear level and a nice clear sound and I can hear it distinctly, I ought to take action. I'm not going to trend ultrasonic as long as I would trend, say, TEV or RFCT detected PD. So I said in the last slide that ultrasonic is affected by humidity. And here's an example, and it's actually a tool we're going to use. If I know the humidity, and I know when the humidity goes up, the ultrasonic level goes up, and when the humidity goes down, the ultrasonic level goes down, I can use that because there aren't a lot of other things that change the ultrasonic activity. So if you look at the red line is the relative humidity, and the blue line is the ultrasonic level. So you can see whenever the ultrasonic's higher, it's related to when the humidity was higher. So, and this is just over the course of several weeks. This is European dates. So, from April 13th to May 3rd, I've got these variations. I've got the ultrasonic level changing. That's going to give me a pretty good indication of what I'm looking at might be PD, not just some other source of ultrasonic energy. So I said the numbers don't mean a whole lot, and don't get too wound up on the numbers, but everybody wants numbers. So we have some numbers we tend to use, and they're more of an indication that if you're really high on the scale, and this is a logarithmic scale, it's related to the voltage that's coming out of the actual detection sensor. And so if I'm down below 6, I'm pretty quiet. And, anything from 10 on up is a problem. Anything above 20, I need to take action right away. And so this is logarithmic, and that 20 is 10 times worse than 10. So these are numbers based on our history. We've tested tens of thousands of panels, and just from, okay, we know that when we get into the 10 plus, there's usually visible damage. You can actually detect the ultrasonic energy from PD before you can see it on the panel, even where it's occurring. Before there's any damage to see, the discharge will actually create a relatively strong ultrasonic signature. So TEV, and I told you this is the one that's the least believable. It took me a while to get my head around it. Imagine we have some high voltage component, and then here we have bus bar, and it's mounted on these orange insulators, and it's inside a grounded metal box. So in this box, I've got some way out of the box, right? Our switchgear is not welded shut. It's not airtight. I've got gaskets, joints, whatever, seams. And so I've got that seam on the top there. And then the box is grounded. And that's a very high strength, high current ground that is very low impedance at 60 hertz. So it's bar stock, it's big, thick cables. That doesn't make for a very good high frequency ground. So when I'm talking 60 megahertz instead of 60 hertz, I actually have a fair impedance. So what happens when I have PD? Well, I start out, I've got this little red explosion looking thing here in the middle of the insulator. I get a current pulse through the insulator from the high voltage to the inside of the cabinet. Now, it won't go through the cabinet because at these frequencies, there just aren't enough free electrons in the metal structure to allow the current to pass. It's got to travel across the surface, which is called skin effect. Travels all through the inside of the box, eventually finds a path to the outside, goes around the outside of the box, and then down through the ground system into ground. Right? That's where our current wants to go. The problem is, well, not the problem, but the phenomenon is when I have a current and this current goes across an impedance, if we remember Ohm's law, current across an impedance generates a voltage. So I get a voltage on the outside of the switchgear. It's typically well under a volt, and it's a microsecond wide. So it's not the easiest thing to pick up. It's also in the presence of all this electrical noise that's going on in the substation. So I need a very specialized instrument to measure it, but basically we're measuring it with a voltmeter. And we measure voltage on this switchgear. We measure it on the outside of a transformer. We can measure it on the outside of a cable sheath, wherever we're measuring it. But if we've got discharge inside a grounded metal box, we can determine through TEV that that's occurring. Like I said, it's not easy to believe, but it does occur. The other thing that happens is similar phenomenon. Imagine I have an overhead insulator. Well, if I have a discharge on an insulator, that current pulse is going to go somewhere. It's going to travel via skin effect, certainly on a steel tower or a tower where the tail ends of the insulators are grounded. Very common that they'll have a ground wire going down a wood pole. You can measure the TEV right on that ground wire. Again, that ground wire is going to have an impedance and it's going to have a current. So if I've got a current and an impedance, I'm going to have a voltage. So I can measure that. Measuring it on an ungrounded wood pole, that's a little tougher, but certainly on any metal structure that's grounded is going to help, or just a ground wire on a wood pole. Now we want to talk about TEV, and imagine we're picking up this millivolt or microvolt level in the presence of tens of kilovolts. Not an easy thing to pick up. What are we going to do? We're going to try and relate two factors. One is the number of times it occurs per second, and that's related to the sine wave or pulses per cycle. Actually, this is mislabeled. This is pulses per cycle and the actual level. And this is again on a logarithmic scale. And so if I've got below 10 dB millivolts of discharge, that is basically it's a 10 millivolt signal. I'm not going to get too worried about that. As I get from 10 to 20 to 30 to 40, and I've got a relatively low pulse count, I'm going to say that that's pretty serious discharge. Possible internals, I get up to 40, 50, that's something you take immediate action on. Now, internal discharge has kind of a limit as to what it can do for pulses per cycle. Let's say it occurs once on the positive half cycle, once on the negative half cycle. I've got 2 pulses per cycle. To get more than that, okay, maybe it occurs twice on the positive, twice on the negative, up to 4. Once I get above 8 or so, it's kind of hard for internal discharge to pulse that many times. Now, surface discharge, if we look at that tracking and treeing that's occurring, every one of those branches on that tree can fire at a slightly different voltage. So I get a lot more pulses per cycle. So 10, 15, 20, 30 pulses per cycle would indicate that it's perhaps surface discharge. If I get a higher than that, it could be background interference, right? And so I want to make sure that I can tell the difference. And then if I have a high pulse count and a very high TEV level, it can be floating metal or contact discharge that I've described. And we want to identify that. It might not lead to failure, but we want to identify that because it's such a high level at times, it could prevent us from seeing low level discharge. So we want to identify it and correct it before we make a determination. So here's a chart. As you notice, all the lines are blurry because there are no black and white things in the world of PD, as it turns out. So I've drawn this intentionally to look fuzzy because I don't want to say that at 9 it's good and at 10 it's bad. It's going to depend on the trends. It's going to depend on the equipment. It's going to depend on how critical it is. If you've got redundancy and all that, I wouldn't get too wound up by 15 dB. If I've got one feed feeding an oil refinery that costs $1 million an hour to shut down, I'm going to get pretty excited about 15 dB. So it does depend on your asset management philosophies. Quick recap on surface discharge and internal. Internal is not affected by PD, as you would expect. It's not exposed to air, where surface is. Internal is lower pulse count, external higher pulse count. You're never going to hear internal because there's nowhere for the sound to get out. TEV versus ultrasonic, obviously. And someone's going to ask me, which one should I do? Do them both. Every time you're doing a survey, do both. Do TEV, do ultrasonic, because you don't know what you're looking for. You're looking for a problem. TEV, we're going to do this test by holding the unit right up against the ground, against the metalwork. And for ultrasonic, we're actually measuring sound. So we want to be looking at air transmitted sound. Touch on cable discharge. So cable discharge occurs typically in terminations because they've done a poor job of terminating the cables, and they've created a high stress spot where the insulation can't withstand the voltage, and you get discharge. That discharge goes down the shield of the cable. It goes out into the air, depending on where it is. It can travel on the surface of the insulator itself, but you get this discharge, and it's very often as a result of workmanship. You know, for those of you on the call that are cable joiners, it's not easy. You're asked to do something that requires hospital cleanliness in a trench, in the rain. So it's not anybody's fault. It's just hard to do. So you see a lot more problems in field terminations. Here's an example, and this is someone's fault. So this black layer is the semiconductor layer. It's supposed to be smooth and straight. There's obviously a right angle cut here. That caused a concentration of electric field, caused discharge. The discharge caused this tracking. You can see the insulation's eaten away along the XLPE insulation, and this led to failure. This was not caught in time. Classic cable termination, workmanship failure. So what we can do is, if I'm looking at the cable and I'm looking at the shield, all right, so I got discharge to the shield, or I have discharge outside the shielded area, but the pulse goes down, is coming from the conductor, and it radiates into the shield. One of those two is going to cause a signal on the shield that wants to go to ground. So if I can put a high frequency transformer, high frequency being it's going to ignore the power system frequencies and just pick up the radio frequencies, I can see that pulse. And often I can see where it reflects off the far end of the cable. If I can see that, I can determine how far away it is. So that's how I'm going to look for cable discharge. And cable discharge is much more common than most of the other kinds. Cable and surface are your two most common discharges. So I'll talk a little bit about our instrument and some of its features. Not that I'm trying to sell you on it. There are other instruments, but it's kind of hard to talk about how we're going to do these tests without talking about the features of the instrument. We have ultrasonic detection, TEV detection, RFCT detection, and radio wave, UHF detection, all built into an instrument. It also detects temperature, records temperature and humidity, so you can get nice repeatable tests. And it also has some built-in classifiers to help us detect stuff in the field that we may not be able to do after one webinar. So some of the interpretation things that you're going to get, and here is a picture of a TEV screen, and we're measuring amplitude, we're measuring pulse per cycle on this particular screen, and we see that we've got a pulse per cycle count of 28. Well, if you remember my last slide, so, well, 28 is kind of hard to get for internal discharge. It's hard to get that high, so you probably ought to be looking at surface discharge. And ultrasonic is much better for surface discharge, so you get this message that comes up and says, hey, break out the ultrasonic equipment, it's time to test for that. Ultrasonic, we have a much more advanced algorithm. It looks at repetition rates, it looks at rise times, it looks at a variety of different things, and it's able to give us a PD or noise indication. Is that 100%? No. But it's another tool in your basket to say, okay, I'm hearing it, I'm looking at the algorithm, I'm looking at the phase result plot, all three of those are telling me it's PD, then it's PD. If this says PD and nothing else looks like PD, then maybe the algorithm got fooled. And it does happen. But this is a really good indication. It gives you a third point to triangulate your decision on whether it's PD or not. I mentioned briefly phase result plots, and this is one of the most powerful things that you're going to find in an instrument. Remember, we're looking at something that's generated by the power system. So if I can generate a plot of where these discharges are occurring relative to the power system, not necessarily relative to the phase angle, because that's very difficult when I'm looking at a cabinet that's got all three phases inside. I don't know what phase is causing it. But if I look at something and say, okay, this is one cycle wide, am I getting discharges occurring half a cycle apart or half a window apart? My window is one cycle wide. And so if I get that discharge on the rising edge and the falling edge, and that's half a cycle apart, I should see two groupings of energy. And this picture on the bottom shows our phase resolve plot where each green dot is one event that occurred at a certain amplitude and certain phase. Well, you can see half a cycle apart, I've got higher levels, I've got a higher concentration. This is synchronous with the power system, and it's caused by something that occurs twice a cycle. Well, what occurs twice per cycle? The voltage peaks. So I've got something that's caused by the voltage peaks, it's synchronous with the power system, and it's generating ultrasonic energy. I've now narrowed down a lot. If I had, inverter noise or I had something else, I would see totally different patterns. And I'll show you some of those different patterns. So a phase resolve plot is a great tool that is now built into the handheld instruments. Temperature and humidity, I'm talking longer than I should. I'm going to skip over that, but you want to measure temperature. You want to record it with every survey. Humidity, you want to record it with every survey you take so you can judge those results in the future. So when I'm taking a TEV measurement, I'm going to use the front of the instrument, which has a TEV sensor built in. I'm going to hold it up against the outside of this grounded metal box that we keep talking about, or I keep talking about, and I'm going to grab that reading and I'm going to look at various different screens to see what it says. So some of the screens, here's that same screen I showed before with a couple different scenarios. So the service PD is the same one. I've got a high pulse count. I've got a very high level. I'm 29 dB. That's pretty high. The next one, I'm at 32 dB, but I'm right around 1 pulse per cycle. So maybe it's only occurring on the positive half cycle. And not every one. It's occurring on 87% of the positive half cycle. That's very indicative of partial discharge. So it's going to tell you that in the interpretation. Here I've got 85 pulses. In the last one, I've got 85 pulses per cycle. That's too high for either internal or surface discharge. So in that case, it's going to tell you this is just too high. It's probably noise. So these sort of things are going to help you use the instrument, especially if you're one of these people that has a lot to do, like most of us, and you don't do this every day. You pick up the instrument after 3 months. These sort of reminders help you remember how it works. We have the phase resolve plot. This isn't a very good plot, but if we had something occurring twice in this cycle window, we could find it with this. Now this picture here, I've got a very low pulse per cycle count, 0.08. I've got a level, but I don't see anything that's grouped together in my half cycles, twice per cycle. So I don't think this is TEV, even though I might have a level of 22, which would put me in the yellow category. I'm not going to get too excited about it. We can also grab waveforms. The TEV waveform is very distinctive. It has typically a rise time of about a microsecond, a decay time of 2-3 microseconds. If you had a leaking arrestor, or you had radio noise, or you had inverter noise, these waveforms would be different. So it's another tool. Remember, we're trying to measure millivolts, microvolts of electrical noise in the presence of tens of kilovolts. So pulling out TEV is not easy. So we really need to be able to discriminate it from other types of sources. I'm going to skip there. Ultrasonic, we've got a variety of different sensors. They're typically airborne, whether it's built in or a flexible one or a parabolic dish that lets us make measurements from the ground. All those are going to help. The contact sensor is something that maybe I have insulated gear where it's weather sealed and I don't have an air path, this indoor-outdoor switch gear where the cable compartment's outdoor. I can put this contact sensor on the door and it's going to translate the vibrations that are hitting the inside of the door into a signal that I can hear. And so I don't have to open that door. I don't have to expose personnel to safety issues. I can use the contact sensor. So I'm going to try and pick up this PD through a louver if I can, through any sort of air path that I can from the source to the sensor. But if I can't, I'm going to use this contact sensor I was just talking about, and that's going to pick it up through the metal. It's going to be a little less sensitive. It's going to pick up background noise. It's not directional because I'm going to pick up vibrations on either side of this metal panel, but as a sensor of last resort, it works rather well. Here's the ultrasonic screen. It looks like the last one I showed you. You've got an algorithm, you've got a level, you've got your phase resolve plot, and you're listening with your headphones. So you're going to try and use all three of those things to tell you whether you've got PD or noise. And previous generation products had headphones, and you listen to the headphones, and if you heard it, you heard it. If you didn't, you didn't. It took a lot of practice and a calibrated ear to determine the difference between PD and, say, Corona. But with the added screen information, you can tell a lot more. Here's the classification, and this is a good example of a couple phase resolve plots. The one on the left is clearly PD. The one on the right, you can see it's random distribution of those green dots anywhere in the cycle. So it's not synchronous with the 60 hertz. It's not occurring twice per cycle. I can look at the phase resolve plot. I'll tell you it's noise. The algorithm tells me it's noise. And I listen through my headphones. I'm sure I can tell you it's noise. So even though it's a level that is 100 times worse than the one on the right, it's not something for concern. So here's an example of some PD. This white spot here is an indication these plastic boots were not called for by the manufacturer, and they added it. You can see a nice phase resolve plot. I've got two groupings of energy, half a cycle apart, and they're 20 times, 100 times worse than the periods in between. Clearly PD. So here's an example of corona. Corona is unique in the ultrasonic band in that it tends to occur more on one polarity than the other. And that's really helpful in that I can see one grouping of energy. It sounds very similar, but it does not look the same on the phase resolve plot. So if I get something, I think it's PD, I can tell whether it's surface PD or corona. If it's corona, I may not do anything about. If it's surface PD, I may. This was actually corona that was occurring inside a metal compartment. Usually you see it out on insulators and poles. Now look at this phase resolve plot. Clearly it's noise, right? I got nothing phase resolved. I've got lots of noise. Well, it was coming from some AC to DC converter equipment. So, lots of switching noise, lots of vibration, lots of other things going on, but certainly no PD. And so we can see it in the phase resolve plot. This is actually the output of the report from the device, and it tells us that it's noise. It also tells us that its classification certainty is 100%. So it's 100% sure it's noise, and so am I. Oops. So here's an example where we found PD. I personally did this. I was on the roof of a freeze-dried food building, and we measured some PD through the door before we opened this. We were there to do a cable test, but we took the instrument as a kind of a personal safety system and said, hey, there's PD going on inside this cabinet. Even though it's dead front, I'm not opening that door. So we got on the proper arc flash gear, got in there, and then we used the parabolic dish and moved it all around these different terminations until you see the picture on the right, and that red dot is from the laser sight in the dish. And if you look a little closer, you can see that white powder. So that white powder is indicative of PD. When we pulled that boot off, we could see that the bushing was damaged, and that boot was full of white powder, which is very indicative of PD. So here the instrument came in handy, even though we were there to do a cable test. Beat this to death a little bit. So cable measurements, we talked about cable measurements, and so we're going to put this RFCT on the cable, and we're going to look for PD, leave it there for a few minutes, and hopefully see what we see. When we're doing a PD measurement with an RFCT, one advantage is we now have polarity. Are the electrons going one way or the other way through that the core of that transformer? So I can give a positive and negative phase resolve plot. I can measure directly. I'm not inferring something from the ultrasonic level. I'm actually measuring the level. I'm measuring 2,633 picocoulombs. I can measure the pulse per cycle. So this gives us a direct measurement. The challenge is, of course, getting the RFCT around the ground strap. Very often we'll use a permanently mounted RFCT where they mount them in the cabinet, bring them out to a test box, and you can then make that test whenever you want. Otherwise, it's going to be very difficult to get the RFCT on live. Dangerous, in fact. So here's some examples of RFCTs installed. These pictures down here are hot stick mounted RFCTs. And this last picture is the good old days where we put our arc flash suits on and went into that cabinet live and hooked up the RFCTs. Don't see that a lot anymore. This picture's from about 5 years ago. It's a lot less common. Permanent RFCTs have had a huge surge in popularity in the last 6 months. We see everybody putting them in. Lastly, we'll talk about UHF. So why are we measuring with UHF? It's radio waves. We can do it from a distance. We can stay back from the electrical insulation. Maybe it's like this picture here. We've got insulators that are not in a metal box, so we can't measure TeV. So if they had internal discharge, we couldn't use UHF. or we couldn't use ultrasonic. We can't use TeV because of the construction. UHF is about the only way that I can pick something up. So it's great. If I have a directional antenna, I can actually use it to localize it, move it around, figure out exactly which insulator is being tested. And Corona does not put out a lot in the UHF band. So Corona won't swamp the instrument. Corona won't give you false readings. UHF is a much better tool to use in the substation than VHF. They also attenuate. UHF signals tend to attenuate a lot quicker, which the disadvantage is you need to be closer, but the advantage is that you can kind of localize. Once you get close to it, you know you're near it. And it's also, it does not work outside metal boxes. So for metal clad switchgear and things like that, it's not going to work too well. It's going to work much better in outdoor substations. Here's an example showing Corona. So this is a spectrum showing the Corona discharge from 100 megahertz to 1,000 megahertz and showing how much the background spectrum increased. And you can see all that energy is all below 300 megahertz. So I don't want to detect Corona. I want to make sure I'm ignoring Corona. If I look at, say, 800 megahertz, then I'm not going to see that, which is great. And it allows you to not worry about mixing Corona with surface PD. So here's a system. It's our system. Again, the same instrument and a directional antenna that makes it a lot easier to localize your PD as opposed to a whip antenna or something like that. A Yagi antenna will work, but that's pretty big, bulky, and dangerous to carry around the substation. Different things you get. You get a 3D phase plot. You get a phase resolve plot, just like all the other stuff. And you can also do a spectral sweep if you want to look at it from 50 megahertz to a gigahertz, so you can see what else might be going on. So finish up with a couple examples. So here is an ultrasonic test detected this. I did this myself in Michigan. They had two different phases going through this weird bushing thing. I've never seen anything like it. Because they were unshielded and because they were touching, that created a high field stress. They didn't control that stress, and they had the discharge. And you can see that white powder that's very indicative. Classic PD, pretty old cables, but they were on their way to failure. Here's another example. This is using the wrong parts, right? I said in the beginning that you could use the wrong parts. I've got these boots. There's nothing wrong with these boots, but you can't put these boots that close together. So where the two boots are coming together, you've got these two circles. You're creating a concentration of field stress. You've got the tracking, which we can see. You've got the white powder, which is the insulation actually degrading and coming apart. And you have a lot of ultrasonic energy. This also created TeV. You can see the rusting on the metal and all the bolts around it. That's from the nitrous oxide buildup is going to cause that, and the ozone is going to cause that. So if you go into a cabinet and it's not wet and you got a lot of rust and then your coppers turn green, start to suspect PD. So here's an example where a customer had some stuff out in the swamp and they never cleaned it, and they had a horizontal brace, as you can see in the left picture, going across there, and they had all kinds of dust buildup. Now, dust isn't conductive typically, but what happens is it traps moisture and holds moisture. So once it did that, the area between the bus bars now had a different field strength distribution. If something's conductive, you're not going to have a voltage drop across it. So then that same voltage drop is going to be concentrated where it isn't conductive. So it was concentrated at the ends of the separation, and you can see where the insulation was eaten into. It was in the process of failure. This was screaming out ultrasonic energy. There was no need for an algorithm or a phase resolve plot. You got near it, it just put out a ton of noise. This was fixable, right? If they went another 6 months, maybe it wasn't fixable. So here's one of my favorite examples. A customer put in unshielded 33 kV cables up to a PT compartment. They laid the cables on an insulator. So if you did a high pot test or you did a Megger test, it would pass. I got insulator on insulator. I got 6 inches to my nearest ground point. I'm golden, right? No, you're not. And this is the subtleties of PD are lost on people that haven't been exposed to it. That sharp edge of that insulator resting against that insulation, just like the picture I showed where we had that inclusion and it changed change the field stress distribution, right at that point, you would have a high electrical field stress and you would have discharge. That discharge would burn the insulation, as you can see in the picture. And they did this 12 straight cables in a row. And you can see every one of them's got burn marks. This is 4 months after installation. And the manufacturer of the switchgear looked at this picture and said, that's installed correctly. So not everybody is up on PD. So here's an example of internal PD, where this is a cast resin CT, and the center conductor here has been removed, but there's a channel eaten through the resin. This is putting out a lot of TEV, would not have been visible. You could have done a visible inspection of this thing and put it back together, and it could have blown up the next day. That's why internal discharge is really hard. Now, it may have taken 10 years for this channel to be eaten, so we don't have to worry about it failing the day after we install it, but we do need to worry about it. Here's another example of a bad cable termination. The termination may not be bad, but the way they've done it, they've got these shielded portions, right? This bump in the cable is where the shield ends, and they've got, on both of these, they've got the unshielded portion too close together. And that's going to cause a high field stress. It's going to cause discharge. We get our white powder, we get our tracking, we get our ultrasonic energy. All this stuff comes because they didn't read the instructions on how to do the installation, and they got them too close together. This is more an environment thing. This is from one of my friends in the Caribbean. This is 6-year-old switchgear, and this surface PD. I took this picture and a pile of it laying in the corner because they had to replace it. They replace their switchgear every 12 years because this PD buildup. Fortunately, they're able to detect it when it's online and make an organized breakdown, an organized replacement, as opposed to waiting for it to break down. You see that tracking, you see the white powder. You can imagine every one of these branches fires at a slightly different voltage, giving us a higher pulse count. So here's a cable termination up at the top of a cable. We've got our phase resolve plot. Really not very good work there. We got TEV, we got UHF, we got a variety of different things telling us there was a PD problem here. This was in Australia. Here's one via UHF. And so this is a phase resolve pattern. It's very characteristic of UHF. The way this equipment was built, you couldn't get very close to it. You couldn't do a TEV test. And so we went in there with the UHF, and we've got 2 groupings of energy, half a cycle apart. Clearly, there's not much else going on except that discharge. So we're not getting interference. We're not getting background. Able to tell rather convincingly that there was something going on inside that switchgear. It was inside, so it wasn't creating any ultrasonic. In this case, UHF was the only option they had. They could have done an RFCT test, but you can see where the terminations are, the cable terminations. They would have had to shut down, install the RCTs, re-energize, run the test, shut down, remove the RCTs, and they weren't willing to do that. Fortunately, UHF was able to find the problem for them. So that's the end of my webinar. Like I said, I can keep talking as long as you have questions. If you want to know more, certainly you can contact us. Next month, there's a Mission Critical magazine. It's got a nice article that we wrote on it. And we also have a YouTube site where we have a lot of videos. We have past webinars. We have ones that specialize on cable PD. We have stuff that specialize on, we have some videos on how to do ultrasonic testing and how to do TEV testing. And of course, you can go visit our website. So with that, I will turn it over for any questions. And if you have any, just enter them into the chat box. I'll try and answer them. Okay, well, I guess that means that either I did a great job or I put you all to sleep. I hope it's the former and not the latter. And like I said, check out our website and our YouTube site for more information, or just call me. I'd be glad to talk about it. Obviously, I like to talk. So thank you. I'm going to end the webinar now. And As I said, you'll be getting a copy of the presentation, and I'll also send out a link once the video is up on YouTube.